Auzubillahiminash-shaytanir-rajim. Bismillahir-rahmanir-rahim. Assalamu alaikum warahmatullah. Welcome to the second lecture of week 5. In the last lecture, we discussed basic principles and process of the forging, and we also discussed some formulas or the numerical methods to calculate the forging force that we required while performing the forging operation. And in that context, we looked at a solved example of our textbook. Now we'll jump towards some exercise problems towards the end of this chapter. So let's start with it. So the statement says a cylindrical part is warm upset forged in an open die. The initial diameter is 45 mm and the initial height is 40 mm. So we have a di that is equals to 45 mm, and we have the initial height of 40 mm. The height after forging is 25 mm and the coefficient of friction, so the height after forging final height is 25 mm. So we have hi minus hf to be 40 minus 25, so we have 15 mm of deformation, reduction in height. The coefficient of friction at the die work interface is 0.2, so we have the friction coefficient of 0.2. The yield strength of the work material is 285 megapascal and its flow curve is defined by strength coefficient of 600 megapascal. So we have flow curve of 600 megapascals and the strain hardening exponent of 0.12. We have a strain hardening exponent of 0.12. Now it says determine the force in the operation. Now we have to determine force in the operation just as the yield point is reached. So when the yield point is reached, we have to find out the force. Then we have to find out the force at the height of 35 mm, and we have to find out the force at the height of 30 mm, and finally at a height of 25 mm to achieve the height of 25 mm. So let's start with the first part. Now we have a cylindrical part, so let's start with the volume. Volume of cylinder would be that is pi d square h into 4, pi d square h by 4. So we have pi into 45 square into h, that is 40 mm the initial height, divided by 4. So the value of the volume would be 63617 millimeter cube. Now it says at a yield point, so we have at the yield point, as we have seen in the last lecture, that if we don't have an exact value of yield point, we draw a line parallel to the stress strain curve. We draw a line at an offset of 0.002 strain and we draw it parallel to the stress strain curve, and the point where it strikes, that is the yield point. So based on that, as the yield point is reached, so we have the strain equals to 0.002, right? Now at this strain, the flow stress value would be equals to flow curve into the strain exponent strain hardening. That would be equals to, we have the flow curve value of 600 megapascals into the strain value exponent 0.12. So the value of the flow curve would be 284.6 megapascals. That is the value of the flow curve. Now we have to, as we know that the force for the forging is equals to kf yf into the cross sectional area. So we know the yf. Now we have to find out the kf and the area. We have the volume, and we have to find out the height because we have some amount of strain here. So obviously it means there's a slight reduction in the height. So our initial height is, as the problem suggests, is 40 millimeter. For the case 1, our final height would be 40 into this strain. It would be 40 minus the amount of strain produced. So we can solve it. So the value is equals to 39.92 millimeter. So this is the final height for this part 1 as the yield point is reached when we have this amount of strain. Now we have the final height, we can find out the area with this height. We have the volume, we have the height. You can simply divide the volume by height to get the area. That is equals to 63617 divided by 39.92. So the value of the area would be 1594 millimeter square. Let's say at yield point. So the area, cross sectional area at the yield point would be 1594 millimeter square. Now find out the value of shape factor, that is 1 plus 0.4 into mu into diameter divided by height. So that would be equals to 1 plus 0.4 into 0.2 into the diameter. Initial diameter is 45 divided by height at that point is 39.92. So we'll have the value of the shape factor equals to it's equals to 1.09. So now based on the value of area and the flow stress, we have this one and the kf. We can find out the force here. So the force would be equals to 1.09 into flow stress of 284.6 and into the area, that is 1594. So the value of the force would be 400 newtons. This is the value of the force just as the yield point is reached. So for the second one, when we have achieved to achieve the height of 35 millimeter, that is less 10 millimeter, let's 5 millimeter, let's do with it. So we have HF now equals to 35 millimeter, right? And we have the strain value. The strain value would be equals to ln of 45 by 35, ln of 40 by 35. So we have strain equals to 0.1335. This is the value of the strain. So based on this strain, you can find out the flow stress, that is Ke exponent n, K strain exponent strain hardening. We have the value of K equals to 600 megapascal, and the strain is this one, and the strain hardening exponent is 0.12. We can simply put these values and get the answer, and that would be equals to 471.2. This is the value of the flow stress. Now as the volume is constant throughout, so we have the same volume, we have the height, we can find out the cross-sectional area at the height equals to 35. So we will have volume, that is 63617 divided by the height, so it's equals to 1818 millimeter square. Now we have to find out the value of Kf, that is 1 plus 0.4 into strain hardening into the diameter divided by h. Now our diameter has also changed because we have a change in area. In this time we have neglected the diameter change because it was really small, but in this case as we have a larger change in the height and cross-section area, so it means we have a greater change in the diameter as well, and we have to identify that. So our diameter would be equals to, we know the value of h, that is equals to 35. We know the value of friction coefficient, that is equals to 0.2, and rest are numeric, so we have to find out the value of the d. And we know the area, so area as we know equals to, for cylindrical body, equals to pi d square by 4. So from here we can calculate the diameter at this area. So the value of diameter would be the value of diameter equals to 48.1 millimeter. So we can put these values in this shear factor formula and put the value of shear factor, cross-sectional area, and the flow stress into the formula, force formula of the forging. We can get the answer directly, that is equals to 950/700 Newton. So this is the force that is required to reduce the height of this cylindrical body from 40 millimeter to 35 millimeter. Now we can move on to the next part. Let me erase this one. So the next part is we have to find the height at 30 millimeter. So the final height here would be equals to 30 millimeter. We know the initial height is 40 millimeter, that is initial height. So we can have the formula, our volume is constant, so the value of the area would be equals to, at h equals to 30, that is 63617 divided by 30. So we have the volume of the area equals to 2120.6 millimeter square, and we have the area. Now we can find out the flow stress, so y equals to k strain into strain hardening exponent, and the strain would be equals to ln of 40 by 30, and that would be equals to that is equals to 0.2877. So now we have the strain, we have the strain hardening experiment, and we have the flow curve, so you can directly find out the value of the flow stress, that is equals to 516.7 megapascals. To find out the diameter at this particular cross section area, we can again use the same method, that is area equals to pi d square by 4. So we have d square equals to 4 into 2120.6 divided by pi. Let me erase this one, under root. So we have the diameter value equals to 51.96. millimeter. Now we can find out the shape factor, that is equals to 1 plus 0.4 into the friction coefficient into the 51.96 whole divided by 30. You can take all the values of kf, cross section area, flow curve, and put it in the formula for the forging force. So our final value for this one would be equals to 124,756 newtons. So this is the formula for the forging force. So as you can see here, as the height is being reduced, the force required is also increasing. Initially we had a requirement of force equals to 400 newtons. Then the force requirement has been increased to 950,000. Then it has been increased to 1,247,000 newtons. So as you see, as we move towards the end of the stroke, we have a requirement of maximum forging force. And why is that so? Because of the strain hardening within the material. So this is some practical example for this one. Now let's move on to the next numerical. So the next problem states that a hot upset forging operation is performed in an open die. The initial size of the work part is d0, that is 25 millimeter, and the initial height is 50 millimeter. The part is to be upset to a diameter 50 millimeter. So our primary concern in this one is to achieve the diameter 50 millimeter. The work material at this elevated temperature yields at 85 megapascal. So it means, as we know that we are performing the hot forging, so we have the strain hardening equals to 0. And we have studied while discussing the hot working or the hot forging that when we are performing the hot forging, we take the flow curve equals to the yield strength of the material. So in this case we have 85 megapascals. The coefficient of friction at the die work interface is 0.40. Determine the final height of the part and the maximum force in the operation. So what's our primary concern? We have to find out the final height. So we have the initial height equal to d0 and the initial diameter equals to 25 millimeter. So first and foremost we will calculate the volume, as the volume remains constant, that is pi d square h by 4. So we have equals to pi, what is d0, that is 25 millimeter square into the h, that is 50 millimeter divided by 4. So the value of the volume would be equals to 24,544 millimeter cube. So this is the volume of this body. Now we'll find out the area. As we know the height as well, and we know the final diameter. We have the value of df also, that is equals to 50 millimeter. So we will find out the area based on this final diameter. As you know that area equals to, we can find out the area using pi df square by 4. So that would be the final area, final cross-section area. So we have pi into the final diameter divided by 4. So that would be equals to 1963.5 millimeter square. Now it says we have to identify the final height of the part. So we have the cross-section area and we have the volume. To find out the height HF, we can simply divide volume by the area. We'll divide the total volume divided by the final area. So we have 24,544 millimeter cube divided by 1963.5. So the final height would be equals to 12.5 millimeter. So this is the final height. If we hot forge this part from 25 to and some 25 diameter to 50 diameter, right? So this is the final height. Now the part B is we have to find out the maximum force. As you know, the maximum force in the forging operation is towards the end of the stroke. So we have the initial height of that is equal to 50 millimeter. We have the final height of 12.5 millimeter. So at this height of 12.5 millimeter, we will have the maximum force. Right. So we will find out the strain at this height, that is equals to ln of h naught by hf. We have h naught equals to 50 divided by 12.5. So the strain would be equals to 1.3863. So based on the strain, we will find out the flow curve, flow stress. We have the flow curve into the strain exponent strain hardening. As it's a hot forging, so we know that the strain flow curve would be equals to the yield strength of the material. In this case, we have yield strength of equals to 85 megapascal. So we'll simply write 85 into 1.3863 exponent the strain hardening, that is equals to 0. So we have flow stress equals to the yield point, that is equals to 85 megapascal. So the maximum force, as we know that towards the end of the stroke, so we will simply find out the forging force equals to Kf Yf in A. We know the cross-sectional area, that is equals to this one. We have the flow stress. Only thing we need to determine is the shape factor, that is equals to 1 plus 0.4 into friction coefficient into diameter divided by height. So we have Kf equals to 1 plus 0.4 into the friction coefficient, and the friction at the work done interface is equal to 0.4, that is 0.4 into the final diameter, and the final diameter here we had 50 as given in the problem, divided by the final height, that is 12. Final diameter is 50 millimeter and the final height is 12.5 millimeters. So we can find out the shape factor, that is equals to 1.64. Now we have values of all the required variables, that is shape factor, flow stress, and the cross-sectional area. So we can directly find out the force, that would be equals to shape factor into the YF, that is equals to 85 into the area. So the answer would be 273,712 Newton. So this is the maximum force in this forging operation. Why it is maximum force? Because it is towards the bottom of the stroke. Now move towards the next and the last problem of our lecture. Now moving towards the last numerical of this lecture, it says a part is to be designed to be hot forged in an impression die. The projected area of the part including the flash is 16 inches square. After trimming, the part has a projected area of 10 inches square. So we have the we have the area of 10 inches square after trimming, and we have the area of with flash equals to 16 inches square. Now it says part geometry is complex. As heated, the work material yields at 10,000 pounds per inch square and has no tendency to strain hardening. At room temperature, the material yields at 25,000 psi. Determine the maximum force required to perform the forging operation. So as we have seen, as we know that it's a hot forging, so we have strain hardening would be equals to 0. Strain hardening would be equals to 0, and the value of the shape factor, as we have seen in the last in this lecture, if you go through the impression die forge for the complex shape here with the flash, for the complex shapes with the flash, the shape factor is equals to 8. So we have Kf equals to 8. So we can directly find out the force, that is equals to Kf Yf into 8. So we have value of Kf equals to 8 and the Yf is equals to 10,000 psi. But as we are considering the shape factor with the flash, so we are considering the cross-sectional area with the flash as well. So we have 16 inches square of the cross-sectional area. So the final answer would be 1,280,000 pounds. So this is the force required to perform the impression die forging. So as we see here, the required forging force has increased drastically. So this is because of formation of flash in the forging operation. So flash, as we have seen, the flash has certain advantages, that it constricts the material within the die cavity, which help us to fill the minor details in the cavity. But on the other hand, it increases the required force to perform the die operation, to perform the forging operation. So that's all for this lecture. Should you have any question, you may reach me at the Google Classroom. Assalamu alaikum.